Okay, so in this video, we're going to talk about something that might have sort of a scary sounding name, might be a little scary for some of you, but it's really not that bad. Okay, and it's the topic of eigenfunctions. Okay, so you've probably heard this prefix eigen in linear algebra, like for an eigenvector or an eigenvalue. And it turns out eigenvectors are, the reason these are called eigenfunctions is because there's a similar sort of analogy to eigenvectors that we'll see at the end. But okay, so this is the general topic, but what's the setup? Well, the setup for us right now at this point in the course is we have some input, okay, to an RLC circuit. And pretty soon we're going to be generalizing this box here to not be an RLC circuit, but to be something called an LTI system, a linear and time invariant system. I know you don't know what that means yet. Just a little bit of foreshadowing that's coming very soon. Okay, so for now though, we're just going to deal with RLC circuits. This is sort of the bridge from ECE 35 to ECE 45 to start by looking at circuits. And this circuit, let's say it has some frequency response, h of omega. Okay, and then we get some output. Who knows what it is? I'll just call it y of t. Okay, we get some output. So this is the general setup. And so now I think we've seen some of this before, but I want to look at a couple outputs to very specific inputs. So what if the input is cosine of omega t for some omega, some frequency omega? Okay, so if that's the input, then what would the output be? Like I said, we may have seen this before, but I'll just go over it one more time. So we can get the phasor and then use the frequency response phasor relationship to get the output phasor. And then we can unphasorize, go back to the time domain. Okay, so if the input is this, then the phasor is, again, I use capital letters for phasors. So what is it? Well, the coefficient is 1, right? It's like I have a 1 right there. And the phase is just 0. There's no phase, right? So times e to the j0. And of course, this is just 1. E to the 0 is 1. Okay, so then we know what the output phasor is. Okay, we know what the output phasor is. I'll call it y. And we know that it's the input phasor times the frequency response, right? That's how we define the frequency response. The frequency response was defined as the output phasor divided by the input phasor, where the input was a sinusoid with frequency omega, right? And so this is a function of omega. Depending on the frequencies I put into the circuit, of course, I can get a different frequency response, right? The frequency response is how the circuit affects an input with that particular frequency. Okay, but keeping in mind that I put in a sinusoid with some frequency omega, this is the frequency response, the output phasor divided by the input phasor. Okay, we're seeing how the output phasor is changed in relation to the input phasor. Okay, so of course, if I just bring x to the other side, then I get what I wrote here. Okay, so the output phasor is the input phasor times the frequency response. In this case, the input phasor x is just 1, so I just get the frequency response. And I'll write that in phasor form. In other words, just the polar form of that complex number, because we know phasors are just complex numbers. And it looks something like that. Magnitude of h of omega times e to the j angle of h of omega. So just to summarize, i.e. that is, if 1 is the input phasor, then our output phasor is h of omega. Okay, just to sum it up in one image, that's what that arrow means. The input's on the left, output's on the right. In this case, it's in terms of phasors. Okay, so what about in the time domain? So in the time domain, what's going on? Well, what was the time function I put in? It was just cosine of omega t. This is my input time signal. And so what's my output? Well, I just have to unphasorize this output phasor. Well, this is the magnitude, that's the phase, and I know the frequency is that omega. So the magnitude is magnitude of h of omega times cosine. What's the frequency? We already know. It's the same omega from the input plus the phase. which is the angle of the frequency response. Okay, and this is the output time signal. All right, so far so good. So that's if the input's a cosine. What happens if the input is a sine? So what happens if the input x of t is actually sine of omega t? Okay, well, we want to, change this into a phasor, and phasors, we have the understanding, the convention that phasors are in terms of cosine. So let's convert this into cosine. So sine of omega t is just cosine of omega t. And if I take my cosine, how do I make it a sine? I just got to shift it to the right by pi over 2. That would turn it into a sine. How do I shift things to the right? I subtract pi over 2 from the time argument. Okay, so that's what sine is. So if the input's that, then the phasor, the input phasor, is capital X, and the amplitude is 1, right? Amplitude is 1 right there. E to the negative j pi over 2. Okay, well, what is e to the negative j pi over 2? Well, that's just a number in polar form on the unit circle, where I go down negative pi over 2 in angle, and I get right there on the unit circle, which is negative j. So this is just negative j. Okay, that's my input phasor. And so the output phasor is just the input phasor times the frequency response at whatever frequency omega we're using here. And so this is going to be negative j times h of omega. Negative j is just e to the negative j pi over 2. Of course, I could have kept that here. I just wanted to review that that actually is just negative j. Okay, times h of omega, which we know is the magnitude of h of omega times e to the j angle of h of omega. Okay, so now I can combine the phases, and I just get the magnitude of h of omega times e to the j, and I have angle of h of omega minus pi over 2. Okay, so just to summarize what we've done there, if negative j is our input phasor, this is what we're saying, then our output phasor is just negative j times h of omega. Okay, we know our output phasor is just our input phasor times the frequency response. All right, so again, what happens in the time domain? So in the time domain, okay, I put in sine of omega t, but then I wrote that as cosine of omega t minus pi over 2. And then I put it through the system, and what did I get? Well, this is the phasor I got, my output phasor. So what is the output time signal? Well, it's just the magnitude of that phasor, okay, times cosine of what frequency are we using? Well, we can see we're using omega, so omega t, and then plus that phase, so plus angle of h of omega minus pi over 2, right? This is my phasor, so that's the phase in that complex number, so that's how I apply it in the time domain. But now I can convert back, because this is just cosine of something minus pi over 2 to the straight, and it's just the same property we said before. When I have cosine of something minus pi over 2, it's just sine of that something. So I can change this back. And I get that when I put sine of omega t in, I get the magnitude of h of omega times sine of omega t plus the angle of h of omega. Okay, so you can see that these two properties, whether I put in cosine or sine, kind of a similar thing happens. You put in cosine, what happens when I get the output of my circuit with frequency response h of omega? Well, the magnitude is multiplied by the magnitude of h of omega, and the angle, or the phase of my cosine of my sinusoid gets the angle of h of omega added. And same thing here. If I have a sine, I get out the same sine, but the magnitude is multiplied by the magnitude of the frequency response at that frequency, whatever omega is. And then the angle of h of omega is added as in the phase. Okay. So these are two properties. And, it's sort of relatively simple of how to get the output from the input, but it's not so nice, right? I mean, you got to remember to multiply and then add in here. And same thing for the sine, multiply by this, and add in there. It's not so great. It would be nice if we could kind of combine these two properties into some really simple input-output relation. So that's what we're going to do, and we're going to use sort of a math trick to do that. So now we will employ a trick using complex numbers to combine these two input-output relations into a single expression, or I should say into a single input-output relation. And you'll see what I mean in 1 second. Okay, so what I'm trying to say here is that we're going to start with cosine of omega t. Okay, and we know that that produces, as an output, this is what we just showed, magnitude of h of omega times cosine omega t plus the angle of h of omega. That's what we just did. We also know that sine of omega t does a similar thing, produces this. Okay. Okay, so now we're going to do something that might seem kind of strange at first, but it turns out it's actually really nice. It makes a lot of what we do in this class a lot simpler to write down and keep track of. What we're going to do is pretend that we actually put in not these two things separately, but if we add them up or we multiply the second one by a j. Now, why are we doing this? Well, this is sort of like what complex numbers do for us. Complex numbers allow us to take two real numbers and kind of combine them into one number. You take the real number plus j times the second real number. You're kind of encoding those two real numbers into one complex number. That's why the complex plane is two-dimensional, because I'm taking two real numbers and putting them into one. That's kind of what I'm doing here. I'm now taking two input signals and kind of combining them into one complex valued signal now, where if I ever want either of those inputs, cosine or sine, I just take the real part or the imaginary part of this complex valued input, right? So if I want the cosine, I take the real part. If I want the sine, I take the imaginary part. And now I'm going to put this whole thing in, and what I'm going to get out is this plus j times that. Right? And the way to think of this is to say, oh, well, if I ever take the real part of the input and output here, I'll get a property I know is true. And if I ever take the imaginary part, I'll get a property that I know is true. Remember, the imaginary part does not include the j. So if I take the imaginary part of the input and output, then this input-output relation is also true. Sine gives me that expression on the right. That's what we just proved. Okay, so we're using complex numbers here to kind of encode these two properties into one large input-output relationship. Okay, so now let's try and simplify both sides and see what we get and see, well, is this actually any simpler? Right now it looks sort of more complicated. Does this become any simpler once we simplify both sides? And it actually does. So what do we get over here? Well, we have cosine of something plus j sine of something. That's exactly Euler's formula. What do you know? We just get this nice clean expression, e to the j omega t. This is Euler's formula right there. What do we get over here? Okay, well, both of these terms have the magnitude of the frequency response, so let's take that out. What am I left with? I'm left with cosine of omega t. Sorry, cosine of omega t plus the angle of h of omega plus j sine of omega t plus the angle of h of omega. And now that input is, stuff inside the parens right there, I can use Euler's formula again. So this is the magnitude of h of omega. And now I have cosine of some x plus j sine of x. So I know by Euler's formula, it's just e to the jx, and x in this case is omega t plus the angle of h of omega. So I'm taking that entire expression inside of the cosine sine and choosing that as my x in Euler's formula. E to the jx is cosine of x plus j sine of x. Okay, but now what can I do? I can manipulate this a little bit. And I can take the e to the j angle of h of omega out. And I can split this complex exponential function up into two pieces. E to the j angle of h of omega times e to the j omega t, because when I multiply those, of course, the exponents add. And now what is this? Well, that right there is exactly h of omega, right? That is exactly my h of omega. And so for this entire expression, I just get h of omega times e to the j omega t. Look at how nice that is. Before, we had to remember if I had sine, then you multiply something out here and you add something in the angle, right? It's a little complicated with cosine as well. What do we have here? Well, we just have a complex exponential function, very simple. And on the right, just multiplying. That's it. Very simple property. Okay, so when e to the j omega t is an input, the output is this. And again, if you ever wanted the two individual properties that we started with, you could always just take real and imaginary parts of both sides and you would recover those two properties that we derived earlier. Okay, so now I'm just going to summarize what I just said. Okay, so in summary, what do we have? We have e to the j omega t goes in. And here I have h of omega. This is an RLC circuit. And out comes the same thing I started with, just multiplied by the frequency response at that frequency. Okay, so if I put in e to the j2t, what I would get out would be h of 2, e to the j2t. Right, using this property, I would get out the frequency response evaluated at omega equals 2, e to the j2t. And if you took real parts of both sides, you would get the cosine property we said above. Cosine of 2t goes in, and you'd kind of like undo everything we did here, and you'd get exactly this, magnitude of h of 2 times cosine of 2t plus angle of h of 2. You can try it. It's pretty much what we did here, just backwards. Okay, so this one line here is kind of encoding those two properties we had above, which is pretty nice. But not only that, the operation we get on the output is even simpler. It's just multiplying. You just multiply this complex number by this function, and you get your output. Okay, so it does two things at once, and it's also simpler, which is really nice. So let me just describe it a little bit. So this diagram represents a mathematical shorthand, as they say. We're kind of combining two things in one. This is sort of a shorthand that captures the two input-output relations that we derived above. Okay, and you might be sitting here saying, wait a second, we have an RLC circuit and you're putting in a complex valued input? That's a little weird. And yeah, this is not something that, we could do in real life. You can't put complex valued stuff into a real life RLC circuit because there's no imaginary, J in real life. Okay, so that's why I keep saying this is sort of mathematical shorthand, because this kind of diagram is representing the two input-output relationships that we derived above that are for real. Okay, so we're going to just pretend that putting complex valued functions into circuits is okay. Okay, now for all intents and purposes, you might as well just imagine you actually are putting that function in, okay, and in terms of the math, in terms of the problem solving. And this is kind of a common theme we're going to see in ECE 45, that complex numbers, while sure they don't exist in real life, okay, they can still allow us to kind of have a cleaner time of studying circuits and in general, as we're going to see soon, studying more general systems, linear time invariant systems. If we work with complex numbers, the name kind of goes against what I'm saying, the complex name, but it actually makes things simpler a lot of the time than just working with real numbers. So that's going to be a major theme in the class, that we're going to do a lot of our analysis in terms of complex numbers, because things work out cleaner and nicer and just easier to work with. Things are easier to work with if you use complex numbers rather than real numbers. And then at the end of the day, if you ever want to take real or imaginary parts, you can totally do that. Okay, so that's the situation here. And this is going to be something that we use a lot. And as I said, we're starting here with RLC circuits to kind of transition from ECE 35, but we're very soon going to study more general systems where it's completely fine to put complex valued functions in. Okay, so it's going to be completely fine very soon to have inputs that are complex valued functions. A little weird for RLC circuits, but we're going to get more general very soon. Okay, and so let me just also make a note of what's actually happening here. So for the inputs of the form e to the j omega t, these are really special functions. They're complex exponential functions. For inputs of this form, the output is really simple. The output is actually the same as the input, but multiplied by h of omega, the frequency response at whatever frequency our complex exponential input was at, right? Whatever omega we have there. Okay, and this idea is the reason why the title of this video is what it is and why this terminology is used. This is why e to the j omega t is called an eigenfunction. Why is that? Well, if you remember from linear algebra, not a big deal if you don't remember this, but if you have some vector x, I'll just make a quick note, satisfying that you take some matrix and multiply it by x, and you end up just getting a scalar times x. Okay, how is this related to our situation? Well, the matrix acting on x is sort of like the system acting on an input, sort of like an input that goes into a system. And what do you get out? You get out that same input just multiplied by a scalar number. That's exactly what we have here. We have an input going into a system. We get out that same input multiplied by just a number. H of omega is just a number for a particular omega. It's just a number. You give it an omega, it gives you a number, complex number. Okay, so you put an input in, you get out that same input multiplied by a number. You can see why the terminology eigenfunction is used, because that's very similar to what happens with eigenvectors. So in linear algebra, the vector x satisfying that is called an eigenvector. Okay, just a little note of kind of why this is called what it is. Okay, so yeah, we're going to be using this property a lot. And more generally, like I said, once we get to LTI systems very soon, which are more general than RLC circuits, and all of this will make even more sense in that context. So we have that to look forward to. But that's all I had for this video. I will see you in the next one.